Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what'll happen when we wring it out. Meredith and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth. Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. The water's all over my hands. In fact, it wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth. And then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jello on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations. Great idea.
Bungee right here, and it's just floating here in weightlessness, and you can see the string here is rather loose, and it's just kind of floating randomly. If I were to rotate this thing on the string around this bungee, and let me do this, you can see that the string pulls taut and stays tight. And the tool continues to rotate around the bungee. In fact, if you look really close at the bungee, you can see that the bungee bends at the point that it's rotating, and it bends toward the tool. And that is caused by the centripetal force due to the angular acceleration of the tool as it rotates around, keeping this string tight and keeping the rotation in a circular motion. It's the same kind of force that applies to the rotation of planets around the sun, or the moon around the Earth, or the space station around the Earth.
So I've got a little bubble there, and that bubble of water is going to float away. But I also have with me 2 bats, which are just like table tennis bats, except these bats are hydrophobic, which means they resist the water, so the water doesn't stick to them. They're like non-sticky bats, which means that you can actually play space ping pong. There you go. We can have games on a Saturday and play space ping pong.
I think you're better at ping pong than I am, Tim.
Now, something else I'm going to do is I'm going to make this bubble a little bit bigger. I'm going to add some water to it, and then I'm going to put in a fizzy tablet and show you what happens when we put fizzy tablets in water up here.
Oh, oh.
So I've got my Fizzy tablet here, and the bubble's nice and close to the camera, so I can show you. Here we go, and I'll pop it in. And there you can see the bubble is starting to grow. All of the gas is being released, but all it's doing is it's making that bubble of water get bigger and bigger, and you can see it fizzing up there.
Everyone very, very impressed with that trick down here on Edim. But putting a fizzy vitamin tablet in water has never been so much fun, I think. All right, that's fantastic. What an amazing, amazing demonstration.
But if I were to rotate this, and let's see if I can rotate it and keep it in your view of the camera. Let's watch what happens. If you look really close, you'll see the air bubble starting to coalesce in the center of the tea bag. I'm going to try it one more time. There's the bubble spread throughout the tea, and if I rotate it, the bubbles coalesce to the center of the tea and eventually form a circle. Why do they do that? Because of the centripetal force spread throughout the tea. The liquid tea goes to the outside of the bags and it forces the air into the center because the air has less mass, less density than the liquid. So the air goes to the center.
Centripetal forces affect things here on Earth, as well as in space. Things like
Okay, I've got it on pause, and what you're looking at is a knitting needle. And I happen to have in my crew preference a couple of knitting needles. And not that we have a lot of time to do knitting up here, but there's some other neat things you could do with them. And so watch this. So here I have a piece of paper, and I rub the knitting needle with a piece of paper. And this knitting needle is a polyethylene knitting needle. It's 8 millimeters in diameter. And now I'm going to take a syringe with a little Teflon cannula. I'm going to squirt drops of water out, and look what happens when those drops of water get close to that charged knitting needle. So this is like a little satellite going around a cylindrical shaped planet. Except the physics here is a little bit different. It's not about gravitation. It's about charge forces. And of course, charges can exert a potential field, as we call it. So it can exert a force at a distance with no tangible connection. And so you have a charged drop that was ejected from the Teflon-tipped syringe. And then you have the charged knitting needle. And they're going to be attracted if they're opposite charges, but because the drop has some velocity to it, it's orbiting around the knitting needle. Now this knitting needle happens to be a little different than when we started out. This knitting needle is made out of Teflon.
Bye.